All right. So the agenda for today is going through over the transformer architecture. I believe Professor Elkins covered recurrent neural nets in the last lecture. So we'll be building on top of that, and we'll be talking about the transformer architecture today. So I'm going to take you through this journey of all of these various components that come together and build up the transformer architecture. We're going to talk about going from the input over to through all of the intermediate steps, right from the input embeddings to the positional encoding, self-attention, which is the core of the transformer architecture, cross-attention, which is again very useful for multimodal use cases, and also in the encoder-decoder architecture that was originally proposed as part of the original transformer paper. We'll also touch upon skip connections, also called as residual connections, introduced in the seminal residual networks paper, probably the most cited paper in all of AI at this point. We'll also talk about layer normalization, which is another critical component of the transformer architecture. Then we'll touch upon token sampling, which is towards the output of the after all of these different steps. And then lastly, I'll summarize by going over the encoder and decoder components of the architecture. So that'll be the final conclusion. And then we'll take some question answers. We'll do some questions at the end. All right. So that's the outline of the talk. And with that, let's get started. I'll start off by going over the, like I said, we'll go over various components of the transformer architecture. And we'll begin with a quick overview of the architecture. So on the left, you have the seminal diagram. You'll see that all around the internet, all around papers. This is the transformer architecture introduced in Attention is All You Need. That was the name of the paper by Ashish Vaswani and a bunch of other folks from Google Research and Google Brain back in 2017. Right, so it's been several years since the transformer architecture. It's created a whole lot of waves in the in AI research, going from NLP to vision to multimodal models. So this is it. This is the architecture at the heart of everything that's going on in AI. And self-attention, like I mentioned earlier, is the core component of this architecture. So we will, this is just an overview. We'll cover each component one by one, like I said, going from the input to the output. But just to give you a very quick idea of the main component of the system, that's the attention blocks that you see here, which is one of the self-attention is the biggest distinction coming in from even recurrent nets, which there were a lot of implementations with attention mechanisms there as well, with an encoder-decoder architecture, particularly the decoder attending to the encoder. So there were experiments with attention, which actually yielded some pretty good results, even with RNNs, which you guys covered in the last lecture. But the transformer architecture utilizes self-attention in both in the encoder-decoder, again, something that the segregation between the encoder and decoder will also touch upon towards the later end of this talk today. But just know for now that self-attention is what drives the transformer architecture. And then in terms of impact that we've seen with this architecture, it's loud and clear. The impact that this architecture has had on the field, whether it's NLP, whether it's vision, even compared with CNNs. We have vision transformers, VITs, that have done incredibly well. Again, these are also self-attention based on the vision side, same architecture, but instead of just taking in text tokens, we essentially take an image, convert it into patches by creating grid of patches across the entire image, and then feeding in each patch after a linear projection into the architecture along with some positional encoding. And like I said, we'll cover each of these blocks. I don't want to overwhelm you guys with all of the terminology, but just know that whether it's NLP or vision, there's been a whole lot of great impact from the transformer architecture. Even with multimodal architectures or problem statements that we have right now, the impact is loud and clear. I think that there might be a question on the chat. I'm not tracking the chat. I can't see it. I just see a quick notification. So if there's anything urgent, feel free to stop me in case maybe the audio isn't clear or whatever, but we can take questions at the end. I'll put in leave some dedicated time for questions. But yeah, coming back to the impact that Transformer has had, multimodal is also another common use case, whether it's text, images, audio, sensor data, time series data. We've seen a whole lot of different use cases unlocked with this architecture. The cross-attention, which is another component that we'll be delving into, is what powers a whole lot of multimodal use cases as well, tying one modality to another. So that's also at the heart of this architecture along with self-attention. So that's a quick overview. Now let's delve into the input embedding. So we'll go clockwise one by one. So we just did the overview. We're going to touch upon the input embeddings next, right? So if you look at the architecture from bottom to top, the input embedding is essentially the first step in this process. So it's foundational in that sense, where the idea obviously behind embeddings is that they are a representation of the input, a semantic representation rather, and the idea is that in embeddings for words that are similar in meaning are closer to each other in embedding space versus concepts that are dissimilar or disconnected are farther away in the embedding space, right? So that is the entire idea behind an embedding, right? A semantic representation of the input. So what we have here at the input of the transformer are input embeddings, and not to be confused with embeddings that are generated at the output and which for the transformer architecture are contextualized, which means the transformer architecture is great at identifying the relationship between the various components of the input. So for example, if you have a sentence, talking about, a set of concepts, it's going to be able to connect the dots between the various words in the sentence and derive these correlations for one word relative to a lot of the other words within the sentence, and thereby create a contextualized embedding at the output, right? Something where polysemy, wherein one word, having multiple meanings. For example, classic example here is bank. Whether it's a bank of the river or the financial bank institution, it's able to discern a lot of these nuances in the input thanks to the contextualized nature of these embeddings, right? Based on the words around the center word that you're calculating an embedding for. So those are the embeddings at the output, but here what we're talking about are input embeddings. And for the transformer architecture, when they first trained the original architecture, they actually started with random embeddings by just creating an n-dot embedding layer with PyTorch, rather TensorFlow, and because Google used to prefer TensorFlow back then, now it's all JAX. But if you look at the code, it's actually initializing embeddings from scratch for each word, and then training that as part of the entire process, right? So you have the input embeddings also being trained while you generate output probabilities at the at the end, right? As you sample one word after another. And again, we'll delve deeper into this, but just know that the input embeddings can be started off randomly, while to kick off the training process. You could also start with, current pre-trained non-contextualized or static embeddings that are available. For example, word-to-vec embeddings. You could start off with that, give it a better starting point to the architecture compared to plain random embeddings, and have that be trained end-to-end as part of the process. So there's various ways to initialize the input embedding, but the embedding obviously is, like I mentioned earlier, the key takeaway here, just to summarize, is a form of the input that is semantic in nature. So once the input goes through various forms of pre-processing, and then further on tokenization, these tokens get converted into input embeddings, which, like I said, per the original architecture, were just a series of random floating point numbers resembling a vector, which were the input embeddings that were fed into the architecture and then trained end to end, right? So that was the entire idea behind the first block here, the input embeddings. And then we have the positional encoding. So if you look at the diagram on the left, you'll see right after the input embedding is the positional encoding stage, right? So now let's discover what this is exactly, right? Now, positional encoding basically allows transformer models to understand the order of various, tokens within the input sequence, right? Note that without positional encoding, that the entire architecture has no notion of ordering within the input sequence at all. It does not understand, whether one token follows another or precedes another. That notion does not exist within the architecture. So these positional encodings had to be added in externally right after you would transform your input into input embeddings. You would add positional encodings, also called as positional embeddings, within this input embedding for downstream processing. And if you compare and contrast this with RNNs or CNNs, those architectures do actually, you'll notice that they do not have positional encodings being injected as part of their flow, for the very simple reason that those architectures do have a notion of order within the input sequence as the input is being processed. So you do not need a separate positional encoding component there. But the transformer does rely on positional encodings for it to understand the order of various tokens in the input sequence. And positional encoding, right from the original transformer paper back in 2017, since then to now, there's been a whole lot of different variations of that have been proposed. We started off with absolute positional encodings in the original transformer paper, which were essentially, they were essentially a very simplistic implementation. Essentially, you were, modeling sinusoidal functions, sine and cosine functions, as positions for, to number the various tokens in the input sequence. And essentially, with every new token, you would add a little bit of a wiggle to that function to make a little bit of a absolute position change as you had one token coming in after another. So this is how the original transformer architecture modeled the positional encoding part. And while it did pretty well, and in fact, if I remember correctly, the original paper actually mentioned that they also looked at trainable positional encodings, learned positional encodings, and they did not see much of a performance difference. But the reality is that we have moved on from there on to other implementations, which I'll also touch upon. The biggest reason behind that was that if you look at a lot of the newer models, newer LLMs that have created waves, for example, Gemini that has about 2 million of token context right now, 10 million already being experimented in research. And to be able to extend a model such as an LLM to large context widths, you do need a positional encoding that is able to generalize to something way beyond the original model was trained on, which is essentially what enables it to have millions of tokens in the context width, right? So that generalizability is something that the absolute positional encodings did not offer. Which is what led to some of the other ideas picking up. And one of the other ideas was relative positional encoding, which essentially, instead of just using absolute numbers to represent tokens, the idea was to make sure that we don't have the model overfit on a whole lot of these positions of tokens via absolute numbers, but instead have relative numbers represent some of these positions for tokens. And so this was proposed back in 2018. And instead of using, like I said, instead of using fixed positions, we could use relative distances. So this actually improved generalization, as you'd imagine, because as you would extend the input to have a lot more tokens, being able to go beyond absolute numbers, which is what it could have been trained on, say if it were a fixed context width, to be able to extend that with relative numbers would obviously per intuition do better. And that's indeed what this particular paper showed us. But it did add that extra complexity beyond just using absolute numbers. So relative positional encodings did pretty well, but then they were superseded with rotary positional encodings, which is what we use today, which have essentially led to a lot of good generalization in terms of context width. This is what a lot of the new LLMs that we hear about and see being introduced, every now and then use. So this is pretty standard in the field. It's called ROPE, short for rotary positional encodings. introduced the row former paper back in 2021. And these enable extending sequence lengths pretty efficiently. And the idea is to basically use a rotation matrix for each position and embed essentially with the embedding that you have at the input, multiply that with a certain rotation matrix, thereby introducing a little bit of a rotation within the input embedding rather than having to add an extra positional embedding separately. So in that sense, they embed relative information for positional encoding directly within the input embedding. So that was ROPE, which is, again, like I said, fairly popular at this point. It is the go-to standard in terms of positional encoding. All right. And then next up, we've got self-attention, which is the core of the transformer architecture. So let's touch upon that next. So on the left, you'll see that we've got a couple of multi-head attention blocks. Self-attention, like I said, it is the core of the transformer architecture. And the idea, the main concept is to allow each word in a sequence to focus on other words, and based on that relative focus, be able to capture contextual relationships for that particular word that we're learning and embedding for. So in that sense, these are contextualized embeddings, like I briefly touched upon earlier, that are being generated within the transformer architecture, and all due to the self-attention mechanism that is at the heart of the transformer architecture. So the idea in terms of implementation detail is to abstract each token in the form of query, key, and value vectors. And essentially, the idea behind this abstraction is that the query is the element whose attention score is looking to be computed. The key is the element against which we compare the query to calculate the attention score. And the value is essentially the element that's combined based on all of the attention scores that are learned in order to form the output. And now let's break that down into some more concrete detail, and note that these are abstractions. So it is up to the transformer architecture to figure out what constitutes a great query, given an input token, what constitutes a great key versus what constitutes a great value. So the idea is for us to offer these degrees of freedom, these 3 degrees of freedom to the architecture, and for it to synthesize relevant queries, keys, and values that would lead to the right token being generated at the output, right? Because training is essentially guided by the loss function in the architecture, and for the transformer architecture, the original architecture proposed back in 2017, which we have here, it is just next token prediction. That's essentially the loss function, right? So that's what guides the model during its training. Is just trying to make sure that the output probabilities that you see here in the diagram are basically telling us that the probability of the next token to be generated, which is the token in the ground truth, which is a token that we expect, has to be higher than all of the other tokens that are present, right, within its vocabulary. So the way the query, key, and value abstractions are learned during the transformer architecture is all guided by this particular loss function, which is essentially next token prediction. And one of the biggest advantages here with self-attention is parallelization. Now, you guys learned about RNNs in the last lecture, and the biggest issue with RNNs was that they weren't parallelizable, right? But with transformers, what you can do is you can compute a lot of these attention scores in parallel across the entire sequence, which essentially enables faster training on GPUs and improved scalability. And if you look at self-attention, I have the equation here from the paper, which is essentially, and don't need to worry about a whole lot of the details here. But I just want to make sure that the audience here today is aware of how a lot of these elements, a query, key, and value, interact together to come up with attention weights, right? So if you look at Q, the numerator on the right, it's softmax of Q of KT. So Q is the query, key is, we just spoke about the element, key is the element which against which the query is compared, right? So that's key transpose along with Q. So this essentially enables us to understand the compatibility between the query and the key. What is the overlap here? right? So when we carry out that dot product, we are essentially calculating the overlap of the query vector versus the key vector transposed. And then that's normalized by the dimensionality of the key vector. And this is just to improve training stability. We then apply softmax on this. So the softmax normalization is applied. Again, softmax we'll touch upon in a lot more detail in one of the later slides. And then this gets multiplied by the value vector to come up with attention scores for that particular input token. And once you have all of these attention scores, essentially that is what you use to fuse together all of these various embeddings for other tokens for relative to this particular input token. And that's how we generate an embedding. Essentially, an embedding for a token is a function of all of the other tokens in the input sequence, right? So essentially, the transformer architecture, if you think about it at a top level, learns to how much to weigh each of the other input tokens in the sequence to come up with an embedding for a particular token. So if you were to summarize all of this, that is the gist of what makes a transformer learn contextualized embeddings. And then, the same thing that I mentioned here in terms of the last bullet here on the slide, the idea is to capture contextual meaning, and this enables it to also, achieve long-range dependencies much better than RNNs, for example. So if you have a long, particularly long input with a lot of tokens, the transformer architecture does pretty well linking, entities that are being, referenced, in a certain portion of the input that were introduced way earlier, within the input, and for it to make a lot of these correlations and understand these long-range dependencies, the transformer architecture does pretty well compared to RNNs. So this is one of the biggest selling points of the transformer architecture, which has led to a lot of downstream success in a whole lot of applications, like I touched upon in the overview slide. So that was self-attention. And now we will proceed to cross-attention, which is, a variant of self-attention, and it is geared towards a little bit of a different problem statement. And if you look at the last slide, right, we had for self-attention, you notice that I highlighted two blocks within the diagram, the multi-head attention and the masked multi-head attention. But cross-attention is essentially the block the block that I've highlighted here, which lets you link the left part of the diagram to the right part of the diagram. And the left part is actually the encoder, right part is the decoder. And like I said, we'll also touch upon the encoder explicitly and the decoder once we understand all of these key blocks within the entire diagram. So I have some dedicated slides for that, so don't need to worry about the left versus the right. But just know that the cross-attention, which is also called encoder-decoder attention in certain papers or certain literature, is what enables the encoder to offer its encoded representation of the input sequence over to the decoder for generation of the output. So that is the entire guiding principle. That's the entire concept behind cross-attention. And the way this, gets implemented is fair and square. It's pretty simple, where the encoder, generates key and value vectors, which we just touched upon earlier, right? Those abstractions. So the key and value vectors are what get fed in via this block into the decoder. So you'll notice the two lines here that connect the key and value vectors into the cross-attention block. And then what we have here are the query vectors, the entire matrix of all of the query vectors that gets fed in from the from the intermediate output of the decoder itself. So the query comes in from the decoder and the encoder comes in from the last block of the transformer encoder, essentially the final output of the transformer encoder. And then this gets fed into every single block of the decoder. So every single block of the decoder here, you'll notice the ends on the side. So there's n such encoder blocks and n such decoder blocks, right? And we call these transformer blocks for the encoder and transformer blocks for the decoder. And the decoder transformer blocks have the cross-attention layer right in between, sandwiched between the masked multi-head attention and the feed-forward layer. And this block essentially, this layer accepts input from the output of the encoder. And these are the key and value matrices that get fed in, from the input. And then you've got your query coming in from the decoder itself, right, at the output of the add and not block, which again we touch upon in one of the coming slides, what the add and not block is. But essentially, it is coming in, the query is coming in from the decoder, while key value abstractions are coming in from the encoder. So that's the idea behind cross-attention. And this, like I said, is also called encoder decoder attention. And the core idea behind this is to integrate the source sequence. And if you look at the original transformer paper back in 2017, it was trained for neural machine translation, NMT, which is the task of converting a source sequence in one language to another, right? So the inputs that were fed in to train this architecture were, was essentially a source sentence that was in a certain language. I believe English to German on the WMT data set is what they particularly experimented this architecture on. So the source sentence was in English, fed in, in parallel, all of the tokens going in parallel for a particular sentence in the encoder. And then the key and value matrices that were generated at the output of the encoder were fed in via the multi-head attention block, in this case, the cross-attention block, over to the decoder as it generated the target sentence in German, token by token, one token at a time. So, and we'll touch upon what one token at a time also means as I get into the decoder, the slide for the decoder. But just know that going from one source sequence to another, and it was machine translation from English to German for the original paper. But at this point, since 2017, we've seen all sorts of different tasks, like I mentioned earlier, that transformers are being used for. So they're obviously no longer limited to translation. But you could have various forms of source and target sequences. You could even have different modalities coming in. So based on, say, an input, which could be a text prompt, can I generate an image at the output? Yes, you absolutely can. They're just two different source sequences, right? So similar to what the original transformer architecture did, converted one source sequence to another, which is also called the task of sequence transduction. Generally just converting one sequence to another. So, you can get pretty creative here and go way beyond just translation. So that's the broader point I'm trying to make. But and what enables some of this sequence transduction is the cross-attention mechanism. All right. And then we've got the skip connections, also called as residual connections, and layer norm. So this is actually the added norm block that I was just referencing in the prior slide. So let's touch upon what this exactly is and what this offers to the transformer architecture, right? So you'll see added norm littered all over in the architecture, and I've highlighted those blocks in red here in the diagram. So skip connections, that is the add part here of add and norm. Skip connections, also called residual connections, they were introduced in deep residual learning for image recognition. So this is a paper back in 2015, one of the most cited papers in all of AI. And the idea behind this particular block was to ensure that the issues with training deep neural networks, where we had a lot of layers packed or stacked one after the other. We wanted to make sure that we had a way to ensure that there was gradient, which is the learning signal during backprop as we trained some of these networks, right? So if these are a lot of words that you're not accustomed to, no worries. Just to summarize quickly, the residual connections are a big reason why we're able to train a lot of these deep neural networks at this point, right? Right now, when you see a whole lot of LLMs, ChatGPT kind of models, the reason why we do not go through as much training instability compared to where we were, before the era of residual networks was essentially due to vanishing gradients and essentially the signal that enables training for a lot of these models. We had a lot of trouble making sure it propagates from one layer to another, right? So residual networks really helped in that regard. And the reason why they were useful was essentially because when you train a lot of these networks, you have the entire loss landscape that, shows up, which is essentially, your loss relative to all of these various parameters. And the idea is to find, a minima, right, within that entire loss landscape, something that minimizes the loss, right? And to make sure that this loss landscape was shaped up well, it was smooth, which is very important for the process of neural network training, essentially called backpropagation, to ensure that we didn't see a whole lot of saddle points, rather points where the loss landscape was flat, and points where we couldn't have our optimizer come out of these flat surfaces within the loss landscape, and thereby continue training the model. Residual networks or skip connections really helped in that regard. And the idea is to essentially take the original input sequence. So you'll see with a lot of these loops that exist in the transformer architecture, right? These loops take in the input right before a particular block. So for example, here with the feed forward block on the left, you'll see the output of add and norm, which is essentially the input to feed forward. That's get taken in, and this gets added to the output of the feed forward block as well. So essentially, you have a copy of the input available, even if your attention heads, say block or overlook certain specific positions, right? So this helps enhance model robustness, and it prevents, over smoothing of the entire loss landscape, and in turn offers training stability and convergence, especially in cases of deep neural networks, which is the case today with all of these LLMs. They are extremely deep neural networks, right? So residual connections or skip connections really helped in that sense. And the other component that powers this block is the norm part, right? So that is the layer norm with the transformer for the transformer architecture. And the reason I mentioned specifically the transformer architecture in this case is because there are a whole lot of implementations available to normalize your data. Batch norm was one of the initial papers that came out, batch normalization. Commonly called batch norm. And then we had layer norm, group norm, instance norm, a lot of different variations that came out. But the transformer architecture specifically uses layer norm. And the idea is that just with any normalization technique, it enables us to have a consistent distribution of data, by normalizing based on the mean and standard deviation, going from one layer to another. So the model doesn't have to worry about the varying distributions of different features or different tokens, as it goes from one, feature to another, process one feature to another, from one layer to another. We wanted to make sure that the distribution stays fairly consistent. So doing a normalization step at every stage essentially enabled some of that. And layer norm in particular made sure that we had, this normalization done within a single layer across the entire feature dimension. And this enabled us to achieve faster convergence. So training becomes simpler. You're able to, train your network faster than you could do it without a normalization block. And, so this was also one of the biggest reasons behind, great training stability that we currently see with a whole lot of different deep neural network models compared to where we were, before residual networks and layer norms. So these were two of the biggest ideas, and they were clubbed together in the transformer architecture in the add and norm block. And then, so now that we have an understanding of some of the core components of the transformer architecture, right from the input embeddings to positional encoding, self-attention, the heart of the entire system, cross-attention that enables the encoder and decoder to talk to each other, infuse ideas from one modality to another modality. And then we also looked at skip networks, also called residual networks, and layer norm, a particular type of normalization that's used in the transformer architecture. Next up, let's talk about token sampling, right? And what token sampling is essentially is the idea of de-embedding the embeddings that get created at the output. So if you look at the highlighted box in red, at that point, right after the add norm, we essentially have embeddings, output embeddings, which have to be converted into a certain a word, a token at the output, right? And note that all of these architectures operate in terms of tokens and not words. So you essentially you're sampling the output token, one token at a time, and also clubbing together tokens in some cases to come up with a word. So that's how the output process works out with the transformer architecture, and a lot of these LLMs, for example, which follow the transformer architecture, and we'll touch more upon that in the decoder slide. But the idea here is to have the linear layer and the softmax layer, which then gives us the output probabilities, which is essentially the probability distribution across the entire vocabulary of tokens. And a vocabulary is essentially all of the tokens that a particular the model is aware of, right? So typically for today's models, unilingual models or monolingual models, we've got 50,000 tokens. Some of the newer models, we're seeing much larger vocabulary sizes, especially if they're multilingual. And something around 250K tokens, for example, is fairly common. So these are all of the unique tokens that the model is aware of, right? So it's essentially selecting the index within this vocabulary to tell us which token it thinks is the most probable, as it generates the output one token at a time. So that is the entire idea behind sampling the, output tokens. And this process is done autoregressively. And what that means is, essentially every token at the output is then fed back in as input along with all of the prior tokens to sample the next token at the output, right? So this token works, one loop at a time, one token at a time to generate something at the output, which is why you notice with ChatGPT, for example, or a lot of the other LLMs, you'll notice words being built one step at a time. It doesn't just give you the output at one shot because it's literally sampling one token at a time and giving you the building on the output, one step at a time. So this is the entire idea behind token sampling. And now, this the softmax layer is essentially what we use here, right? So that's a normalization function. The linear layer is used to transform the embeddings at the input, which are the output of the final add-on block across all of the transformer layers. The output at the end after the last add-on block gets projected into a dimension that is essentially the vocabulary of the transformer architecture. And this then gets fed into the softmax function, which is a normalization function. So the job of the softmax is to make sure that it generates a probability distribution that sums up to 1, which is the requirement for a probability distribution, because probabilities can never be more than 1, and the numbers have to be non-negative, right? So they have to be between 0 and 1 for each of the tokens across the vocabulary. So to generate that probability distribution is why we use the softmax function to help with that normalization and transforming the output of the linear layer into a probability distribution and output probabilities, which we then sample from. Now, to go from a probability distribution at the output to a particular token, which is essentially the next token that we're looking to generate at the output, that mapping can be done in a lot of different ways. There's a lot of different methods that let us go from the output probabilities to the actual token that gets generated. And if you look at the last bullet point here on the slide, I've listed some of those methods, right? So greedy sampling, for example, or greedy decoding, as it's popularly called, is a very common method. And essentially, the idea is to just select the token with the highest probability within the entire probability distribution sequence, right? So that's all greedy does. And it just, in technical terms, in code, it does an argmax. So it picks the argument of the token with the highest output probability, across the entire vocabulary, and that becomes your output token, right? Beam search is another option where it maintains a list of tokens at every step to the output. In a lot of the cases, way better than greedy, which does not do any such thing. It does not maintain a set of tokens at every sampling step. In fact, like I said, it's plain and simple, just picks the token with the highest probability in the entire distribution. And then you've got top P, top K as well, and min P that was recently introduced. And so these are a lot of various methods. Top P is also called nucleus sampling. So you've got a certain probability mass that you're looking for. So you accordingly figure out the number of tokens you want to consider in the output, in the probability distribution that are around that probability mass in terms of the cumulative probabilities, summing up all of their individual probabilities. So if these are 5 or 6 tokens, for example, that to put together, each of these put together sum up to say 0.8 or 0.9% of the total probability distribution. You'll then look at these tokens and then sample from them, right? And I have a lot more detail on, I have a primer that I've written to go into each of these methods in a lot more detail. So if you're interested, you could look up, the token sampling primer on aman.ai, where I have a lot of primers on NLP and transformer architecture and a whole lot of different concepts. If you want to delve into some of these areas, but just at a top level, top K is another method which essentially looks at a set number of tokens. So if you say set K equal to 5, for example, right? So it's just going to look at the 5 tokens with the highest probability and then sample from that particular set of 5 tokens to generate your final output token, right? So MinP is another one recently introduced, and I have a detailed summary of MinP on my token sampling primer as well. So feel free to take a look if you would like more detail in these areas. But just to give a very quick overview and not to detour from the transform architecture as much, there's a whole lot of different methods that enable token sampling at the output. Greedy is the most common. That's what we see very commonly, when we deploy a whole lot of these large language models. So this is the default choice. But there's obviously a whole lot of different options to explore and go with. All right, so that was token sampling. And then we have the encoder, which, like I mentioned in earlier parts of my talk, so the transform architecture here, the original architecture uh, had 2 parts. It was actually an encoder and decoder architecture, right? Like we briefly alluded to earlier. The part on the left, highlighted in the red box, is the encoder. And the idea behind the encoder is to synthesize a contextualized embedding of the input that enables us to understand the input and be able to carry out arithmetic operations with that embedding, right? So you could do a whole lot of operations to understand what this particular input is once you have the embeddings. And whether it's tasks like sentiment analysis or classification tasks, you want to understand if there's a particular review written about an item. Is this a positive review or a negative review, for example? So basic tasks like these, for sentiment analysis or basic classification, we could do that pretty easily with the encoder embeddings at the output, right? And the way these are trained, and BERT is actually the architecture that made the encoder fairly popular when it was introduced back in 2018, just a year after the transformer architecture. They essentially BERT use only the left piece of the transformer architecture, and generated embeddings that we could then utilize to do a whole lot of, like I said, basic classification tasks by adding another linear layer on top. And the idea was to train this with a new set of tasks, because like I said, the original architecture, the transformer architecture with the encoder and decoder, like I briefly touched upon earlier, was trained with just plain next token prediction loss, right? All you were doing is figuring out the next token that needs to show up in the output sequence for you to carry out your desired task. It could be translation or it could be another task. But with encoder, what we did was BERT did something called as masked language modeling. MLM is what it's briefly called. And that essentially carried out, the idea here was to mask out certain words in the input sequence and have the model predict those words and in a self-supervised way, right? Train the model in a self-supervised way to make sure that it predicts the right missing word, right? So you already knew which word existed at a certain location within the input sequence. You just masked it and then trained the model by making sure it predicted the right word in its place, right? So this is where the self-supervised learning paradigm came in for the encoders, and that enabled us to come up with embeddings at the output, which were essentially in plain speak, they were vectors for each word that carried semantic meaning, right? Because if the architecture knew and the model knew which word needs to come in at a certain location in a particular input sentence, the idea is that it essentially has some notion of how certain words are used in what kind of context and what kind of meaning do they offer, right? So that is how BERT came about. That is how the transformer encoder became popular. And we've seen a whole lot of new models since then. Roberta was another landmark model that built upon BERT and trained a lot more data because it said BERT was undertrained. And then that further made encoders or embedding models pretty popular. And we've got a whole lot of new embedding models now. And as you'd imagine, with these embeddings that are semantic representations of the input, we are able to carry out a whole lot of different use cases, right? From finding similar items, for example, when you go through your feed on Facebook, Instagram, or even on Amazon, you're going through products to understand which item is similar to other such items. That similarity search is essentially an application that gets unlocked with embeddings. So embeddings are utilized in a whole bunch of different ways. And BERT, which coming back to BERT that made a lot of this popular. BERT was trained on book corpus, which was a data set of 11,000 books, as well as English Wikipedia as well. So they put together a data set of about 3.2 billion tokens, amounting to about 2.5 billion words, and then carried out mass language modeling, which we touched upon earlier, by masking out certain tokens and then predicting them. And this essentially enabled, the creation of great embeddings at the output. Embeddings that were contextualized. So these were different from some of the embeddings we'd seen prior with some of the earlier systems that lacked context, right? So that was the transformer encoder. And then lastly, we've got the decoder, which is the right portion of the transformer architecture. And the idea behind the decoder is to carry out generation, right? So with a lot of the LLMs that we see right now, most of these, if not all of them at this point, follow the classic transformer decoder architecture. So when you look at Llama, for example, or look at one of the GPTs, even though they have a little bit of a variation with a mixture of experts architecture, which is there are some more nuances there. So don't mean to oversimplify the entire GPT architecture. But the idea is that it is the core idea of the architecture is a transformer decoder at the end of the day, which enables some of that output generation token by token as you interact with ChatGPT. So generative tasks are what decoders are great at. So when we say generative AI, this is the leading architecture right now, the decoder. And the idea is to generate tokens one after the other in an auto-regressive way. So every time you have a token at the output, feed that back into the input along with all of the prior tokens, and then generate the next token, right? And this carries on and on in a loop. That is how ChatGPT gives you an output at the end of the day, like I mentioned earlier. So this is the prevalent architecture that we have. This is the most common architecture for, like I said, almost all of today's LLMs. There are a couple of other architectures right now that are coming up. It's state space models, for example, SSMs. So there's some other architectures too that the field is currently investigating, but the transformer decoder is by far the most popular. So, and a lot of the details that we covered today, so we're nearing the end of the talk. Happy to take on questions in a couple of minutes. But just to, I know we covered a whole lot. There was a lot of detail in every single slide. So what I've done is I've put together a whole lot of this detail in a primer, which is available at the URL that I've listed down below. I think we'll also be sharing slides offline, so you'll get the URL too. But feel free to take a note. And I've put together a whole lot of different observations and content about transformers to understand the architecture better, to understand the underlying math better, to understand how transformers perform relative to RNNs or CNNs in text use cases, vision use cases. So offering a overview of that, and a whole lot of other resources and pointers beyond the primer itself. I've linked within the primer to understand various pieces of the transformer architecture. And yeah, with that, we are at the end of the talk. Happy to take on questions. I'll have to wrap up in 6 more minutes at 5 p.m. Pacific. But yeah, let's get started if you have any questions. I'm gonna stop sharing. All right. Any questions? And I know there was a lot of detail in each of the slides. This is a very extensive architecture to cover in a talk, but I've tried to squeeze in a whole lot of information, segregate each piece, and then go over it in sufficient detail while still having to gloss over a lot of the under the hood implementation details. But my primer does have a lot of the low level detail if you're looking to implement the transform architecture in code, for example, or looking to understand specific bits of the attention architecture or input embedding, cross attention. Got a whole lot of information there as well in case you want to look up anything offline. But if you have any questions, happy to take them.
I think, friends, you can ask anything. Like, so he's the head of generative AI team at Amazon, so he's the right person to guide you if you want to deep dive.
Yeah, I spent a lot of time doing generative AI. Happy to, and you can reach out offline as well if you have questions, anything that you'd like more detail in. Happy to send some pointers your way. So feel free to write to me if there's any specific questions. But yeah, we can spend maybe another minute or so and see if there's questions. Otherwise, we can wrap up.
Yes, I have a question.
Sure.
This more in a broad sense. I hear the term Hugging Face a lot. What exactly is Hugging Face's role as a resource for LLMs and other techniques or tools?
Yeah, that's a good question. So just in the way you have GitHub, right, to which essentially puts together a lot of code repositories from developers around the world. We've got Hugging Face, which is an equivalent of GitHub, but for AI. So people, as they put together, they train models and have, code bases around a particular model. They create repositories on Hugging Face. So on Hugging Face, you'll find a whole lot of pre-trained models that you can leverage off the shelf pretty easily with just a couple of lines of code, right? So people, it's a crowdsourced platform, right? So people submit a lot of their pre-trained models along with code, and then you can use the transformers library from Hugging Face and load these models pretty easily, like I said, with just a couple of lines of code. In fact, they give you a lot of the couple of lines with every model as well. So all you have to do is copy paste those lines from the particular Hugging Face page for that model. And they actually have much more than models. It'd be a gross understatement to just say that it's just a model repository. They've got data sets, they've got papers that they index on a daily basis from archive and other platforms. So you can see a whole lot of innovation happening in AI, sorted by timelines, right? Or even collections where if you're looking to delve into, say, speech processing or computer vision or text processing, they've got papers organized in that sense as well, based on the modality, so you can delve into a particular area. So Hugging Face in that sense it's a platform that has enabled a whole lot of open source AI research by getting all of these key elements in one place, whether it's the model, the data sets, or papers, research, a whole lot of these bits. So it's a pretty useful platform. And like I said, if you want to get started with utilizing some of these models, it's the easiest way to use an off-the-shelf model trained by somebody and just try it on some data that you have, for example. So yeah, hopefully that gives you some idea of the motivation behind Hugging Face and what that enables for us AI researchers. Cool. Any other questions? All right. Great, then we can wrap up for today. Dhruval, are we all set?
Yeah. So thank you for such an informative session.
Absolutely. Yeah. All right, folks. Best wishes and take care. Bye-bye.
Thank you.
Bye-bye.
Thank you.
Thank you.
Thank you.